In this video we're going to look at working out the numerical Vega for the option strategy for a butterfly strategy. So Vega for the butterfly option portfolio. So let's abbreviate a little bit. Butterfly. Okay, so we have worked out the value of a butterfly, and we've done so with specific parameters, and we want to rerun the valuation of a butterfly, of both butterflies, but for different stock prices. Now what's obviously different between each of these is we have here sigma equal to 0.1999, and beneath we have sigma equal to 0.2, and the difference is 0.0001 and adding 0.0001. So it's, if you like, the butterfly revalued for just a slight difference in volatility. Okay, so we want to do a data table again and do it simultaneously for both butterflies, and keeping in mind both butterflies are estimated for different volatility levels. So we go to Data tab, What If Analysis, Data Table, and on the row input nothing. On the column input we'll put in the original reference for the stock price. And before I do that, I have to make one change here. I must make this cell here equal to the cell here. So when we change here, let's say this went to 100, this also changes, and these two cells also change. So if I hit return, you can see both updated. And you might also observe that the option with the higher volatility, the butterfly portfolio with the higher volatility, is now worth more. So we're going to see some dynamic behavior taking place. Again, this cell is equal here to C12, and this cell here is equal to C25. So let's revalue both of these butterfly portfolios for the different stock prices. Okay, so we'll say data, what if analysis, data table, and the column is going to be revalued and denominated as the different types of stock. And so we observe now different values of the butterfly, of the respective butterflies. And now we want to work out the numerical Vega. To work out the numerical Vega, okay, we have to use this configuration. In other words, the change in the value of the call for the single option with respect to change in the value of sigma. And again, we're thinking in terms of option Greeks. And we're going to the Wikipedia entry for Black-Scholes option Greeks. Keeping in mind what is the definition of Vega. The value of Vega is the difference of the change in the value of the option with respect to change in the value of the volatility. But in this instance, it's not a single option position, it's actually a portfolio of options. Okay, so let's go back to our spreadsheet. And let's copy that and go back to here and say, okay, what's the change in the value of the option? Okay, so we're looking at, we have two different option positions, or portfolio option positions, with a higher level of volatility and the lower level of volatility. Let's just take this cell and say equal to this value here. And let's go F4 and pull down. And likewise here, equal to this cell reference here, F4 and pull down. And so to calculate the numerical Vega, we simply say equal to the change in the value. Now, I suppose I should say the change in the value of the butterfly with respect to change in the value of sigma. So that would be equal to the higher value, or we could start with, yeah, okay, the butterfly with the higher, associated with the higher sigma, minus the lower sigma, divided by the higher sigma, minus the lower sigma. And what we'll find is, in some instances, the values will be negative and some will be positive. Okay, so let's just check this. And let's graph. So we'll say insert scatter, and let's, okay, we could use this, but let's select data, and it's just simple to remove and say add, and we'll say numerical Vega, and on the x-axis the stock prices, and then on the y-axis the numerical value of the Vega. And then hit OK. And maybe we could do something to the design. So we'll take perhaps this one. And then on the axis here, stock price, or the value of the asset, the underlying asset. And then on this axis here we have numerical Vega for butterfly. And maybe redimension a little bit, just to give additional space. So what do we have? Well, it says if we increase the volatility, let's make it bigger again. So what we have is the following. We have a numerical Vega for the butterfly, and what the Vega is reading or indicating is if we increase the volatility, where the middle exercise is 100, so if we increase the volatility, the value of the butterfly actually falls. But if we increase the volatility close to the lower exercise and the higher exercise, in fact, well, the lower exercise is 80 and the higher exercise would be 120. But if we increase the volatility beyond the upper exercise or the lower exercise, we get an increase in the value of the butterfly. But when we're at the middle exercise, the value of the portfolio, the butterfly, falls. To compare that against if we graphed for a moment, let's take this and graph again the different butterfly values for different exercise prices, go to insert our different volatility levels. What we observed here was the value of the butterfly for different volatilities. If we increase the volatility close to the middle exercise, the value, so if we go from 10% to 20 to 30 to 40 to 50, the value of the butterfly falls. However, when we go lower than the lower exercise and increase volatility, the value of the option increases. And likewise, beyond 120 this side, as we increase the value of the option, as we increase the value of the volatility, the value of the butterfly tends to increase as well, particularly here and here, most noticeable. Okay, so this is an interesting way of viewing gambling on volatility. If you wanted to gamble that you will get a payoff as volatility increases, one possibility is to set up a butterfly but reverse the position, so you have a reverse butterfly, and set up the strategy where the middle exercise is close to the current stock price or asset price. In the next video clip, I will work out the value of the analytical Vega for the same butterfly portfolio, and I'll save this as butterfly numerical Vega for butterfly 2.